So we need to work with numbers. That's what we're gonna do. We're gonna start in section 1.1. I don't have your tests that you took graded yet. I thought I'd grade them all this morning. I got in here really early and I got third period done, and that's all I had time to do. But it did give me some information about probably where you guys are at too, and so we'll get started, and I'll have those for you next time, I'm sure. All right, so we have to use numbers, and you can see this big orange box represents all the numbers that there are. Okay, and there's a set called the imaginary numbers, which I haven't really explained and got into because we're not going to use them right now. We'll use them later, but not right now. So there's some numbers, the imaginary numbers. We won't be using those right away. We're going to be using is the real numbers, which are the numbers you've always used. You might have used imaginary numbers like I. Anybody use the imaginary number I? No? Okay, so you haven't. So you've always used real numbers, so that's not going to be a big surprise to you. We're just going to break them out into smaller groups, and you know like what the names of the groups are. So if I say integer, you know what I mean. Okay. So we'll start with the. I want to call it smaller because that implies something that's not true. But there's this subset of this other larger, this other set, and this set here. And so let's take a look. The natural numbers, the simplest ones. It's like you could call them counting numbers, right? You could have 0 of something, you could have 1 of something, 2 of something, 3 of something, and you can just keep on counting, okay? And those are the natural or the whole numbers. The integers, okay, so some integers are whole numbers, right? But some integers aren't whole numbers, so they're outside, right? So the integers, it includes 0, 1, 2, 3, all those are integers. But also -1, -2, -3, and on in that direction as well. Okay? So included in the integers are these numbers, but in addition to those numbers are those whole numbers that are negative, right? They're not partial numbers. So then we have the rational numbers, which some rational numbers are natural, some of them are integers, and some of them are just rational. They're not either one of those. Okay? So a rational number, we could deduce by the word ratio that's in there. They're the fraction. Okay? Now, are these fractions? Aren't they?
Yeah, actually.
What fraction could 2 be?
2 over 2.
2 over 2 is 1. 2 over 1, 2 over 1 is 2, right? Or we could represent it as a different fraction, right? The 1 could be 2 over 2. We could represent it that way. We could represent 2 as 4 over 2, right? And that could be, it's a whole number, but it's also could be represented as a fraction. Or you could just take any whole number, write it over 1, or any integer, write it over 1, and yeah, it's a fraction. It's just over 1, okay? So here's some that are outside of that, like 3/4. That's not an integer, it's not a whole number, but it is a rational number. It's, okay, the definition of a rational number is any number you can write as one integer over another. Okay, we say integer rather than whole number because we want to include negatives. So you could have 3/4, -7/6, 1/2, 2/3. Like these are all rational numbers. You can write them as one integer divided by another integer. You could also say 0.5. That's a rational number because you could write it as an integer divided by another integer. So 0.5. 2/3 is 0.6 forever. 0.6 repeats itself forever and ever and ever. 2/3 is can also be written as 0.6 forever. So 0.6 forever is also a rational number because it can be written that way. Okay. So all the rational numbers are any terminating decimal, any decimal that ends. So like 0.3576239 stop. That can be represented as one integer over another. Or any decimal that goes on forever but has a pattern. It has just a repeating pattern. If you're going to express it as if there's a repeating pattern in there, you can find an integer divided by another integer that will give you that decimal. Okay, so those are the rational numbers. And then you have irrational numbers. Does anybody know an irrational number?
I can never think of the right words to describe it. It's a number that you can't simplify into a single term, if that makes sense. Like it has to be, it never ends in a decimal place or such. It just continues onward and never simplifies.
Right, yeah, so the rational numbers are ones that are decimals that go on forever, but they repeat, so they're rational. So irrational ones would be go on forever, but they don't repeat.
Is pi one?
Pi is an irrational number, yeah. Pi is an irrational number. There's a number e, there's another number. There's a number called phi, that's another number. There's lots and lots of numbers that are irrational. Okay. And these letters just represent numbers that are irrational. You cannot write as one integer divided by another integer. Okay? So that's a brief overview. So it'll be useful if I can say integer and you know what I'm talking about. Right? Positive or negative, but not like a fraction, like a piece of a number. An entire number, either positive or negative. Like when I talk about rational numbers and they say one integer divided by another, if you know what integer means, then that makes a lot more sense. Okay? So the real numbers have properties, and we'll talk about those properties. Okay? And undoubtedly, you'll ask me questions in the future, and I'll come back to these properties and I'll say, well, you want to know the answer to that? I'll tell you, well, we have commutativity. So either yes or no to your question, right? That's what I'm going to come back to what these properties are, and I'm going to refer to them and remind you of them and ask you to deduce your own answer. Okay? Help you get there. Okay, so closure. Let's start with addition. Let's say if A and B are real numbers, then if I add A and B, a real number plus a real number, what will I get? What's that?
A real number.
A real number. Okay, that's what closure means. If I add a real number plus a real number, I won't get an imaginary number somehow. I'll get another real number. Okay? This works for multiplication as well. So A plus B would be a real number. Real. And A times B would be a real number. Right. Commutativity. A plus B is equal to B plus A. Commutativity. What's the root word of commutativity?
Community.
What? What is it?
Community.
Community?
Yeah.
That's close, but it's, and they might be kind of related, but it's not commune, it's commute. Commute. What does it mean if I say like something commutes? I commute or you commute? What are we doing? What? We're doing what?
Traveling.
Traveling, yeah. If I commute, I travel. I move. I physically move. Do you see why that might be a useful root word to have in this property? Because what happens? What happens with A and B? They move. They actually switch places. They commute. Okay? And of course, multiplication is commutative as well. Associativity. A plus B first plus C. So let's say A and B and C are real numbers. Then A plus B plus C is the same as A plus B plus C. What's the root word of associativity? Associate? What does it mean to associate? What do you think of when you think of associate? Associating, like grouping. If I say that I associate with that person, it just means I like talk with them and exchange ideas with them and maybe hang out with them and do things with them. Okay? There's that movement implied in that. I can associate. If these three people are here, these two people could associate, and these two people could associate. They don't have to go anywhere. They just turn to each other and start associating. And that, for me, that's how I remember the associative property. These two guys can turn and talk to each other first, and then bring C into the conversation. Or B and C could associate first, and then A could be added in as well. But the result is the same, right? And this kind of reveals the truth about the way we deal with numbers. It's 2 at a time. This number plus this number, that's it. You can't really do 3 numbers together. You know what I mean? You only add 2 numbers together, get the result, add it to this other number. Take that, multiply it by this other number. 2 numbers interact with each other by way of addition or multiplication, and that's it. Okay? And multiplication is associative as well. So you know this, you know these things, you know these are true, but there will come a time when I answer your question by referring back to one of these properties. Okay? So, any questions about any of that? Okay? How does this feel? Like review? Okay? It's feeling like review. Feel boring? Bored? Come on, tell me you're bored. Okay. Just based on this period 3's test, but you could all, there's plenty of you who could benefit from, just little snippets that you could take out of this. Okay? Somebody could maybe use that commutativity, associativity thing. Some of you could use, the knowledge of what integers are. So just be patient with me and with each other. We'll get through this and we'll get to more interesting things pretty soon. All right? So let's keep going. Why did that happen? Why? Well, let's just keep it going. And I'll say that let's say that if A, let's say A and B and C are real numbers, then A times B plus C is equal to, what is this called? And I multiply a number by parentheses like that. Distributed property. So what would the result be? What do I do with this A? What does that mean when I distribute? Multiply it by everything in there, everything in the parentheses. So A times B plus A times C. A times B plus A times C. You'd probably be a little more familiar with something like 5 times x plus 3. 5x plus 15, right? That's something that you usually do more often than something like that. But this is general. Any real numbers will behave like this. Okay. To help you see a visualization of this, a little bit of a proof of this, one way we can represent multiplication is to look at the area of a rectangle, right? So if I had x and y. X is this side and y is this side. One way I could visualize multiplication is x times y is the area of this thing, right? This inside is x times y. Okay, so that's a nice little visualization. Okay, so we have that. We have multiplication here. We have one side multiplied by another side. Okay? We're all good on that? So we're going to do it this way. I've got a rectangle here. This will be A. Let's say that from here to there is B, and from here to there is C, just so they can all be kind of distinct looking amounts. Okay. Well, so how big is this side? B times C? B plus C. B plus C will give you this side, and A is clearly just that side by itself. Okay. So this is B in width, and this is C in width. Okay. So if we look at the area of the inside of this, then, well, how big will this area be?
About 1/3.
It'll be A times B. Whatever it is, it'll be exactly A times B. And this will be A times C, because this is also A, so A times C. And so what will the total area be?
AB
plus AC. So that's your distributed property. I think most of you are pretty strong on that. Maybe some forgetfulness about getting this second term involved in the distribution. That happens a lot, just slips your mind. Maybe if this was a negative 5x, or negative 5 times x minus 7, okay? This could become a problem because of the negative. You just let that slip your mind too. What would this, when you distribute it, what would it be? Plus 35. Most of the time, the mistake made there in not distributing correctly is not conceptual, but just going too fast. Just gotta slow down and stay calm. Now we'll talk about. Okay. So what I'm about to do now is do a review of all the fractions that you've learned until this point in which you should be able to do with them. And if you need to ask questions, please do. Okay? But at the end of this, it's going to be like the last time that I formally take time in class to teach you how to whatever with fractions. Okay? Now fractions will come in and we'll use fractions in other capacities and we'll throw like variables into fractions and deal with them that way. But I'll just be referring back to what you already know about fractions. Okay? And I know fractions is a tricky subject, and so don't be afraid to stop me because this is the last formal class time that I'll formally explain the whole thing again like you don't know. Right? Okay, that's what it is. All right. So if we were to have something like 5/6 plus 3/4, what do we need to do? Is that common denominators? Common denominators. Yeah, common denominators. Who would, and I'm not asking you to do it, so raising your hand is not volunteering yourself, but who would feel comfortable coming up and explaining why you need to get common denominators, not how, but why? 2, 3, 4, 5. Okay? So why you need common denominators is more important than how do you find common denominators. Okay. So who would feel comfortable? You don't have to come up here. Just give us a little spiel about why do you have to find common denominators. It's more complicated than you can't add them together until you do. Right? So who's got something? Full explanation, half an explanation? That's okay. Okay. Well, what is 5/6? Let's answer that question. What is 5/6?
5 parts of something split into 6.
Exactly. 5 parts of something, and that something is split into 6. The whole thing consists of 6 smaller pieces. And if you took all 6 of them, you'd have the whole thing. So 5 of them is this much.
Please excuse the interruption. Please release volleyball students at this time. Please release high school
Luck.
volleyball students. Thank you.
Upset spike. Dig. Pancake. Uh-huh. You know what pancaking is?
Nope. I know big spike is down.
Why aren't you playing volleyball?
Cause I'm running cross country.
You can't do both?
No,
How does my dad feel about that?
he's not.
Mad about not playing volleyball?
Yeah.
Oh. Well, I just pretty much do whatever he does. He's scary. So I'm mad at you too.
We're all mad at you.
Okay, and so by the same reasoning, 3/4 is 3 things, three parts of something that's cut into 4, right? Is that what you said?
Yeah.
Yeah, okay. You said it, don't shake your head at it. Confuse yourself? Okay. All right, so here we go. Now, maybe when you go to add fractions, if you just go at it and not know what you're doing, you might do like add 5 and 3 and get 8, 8/10, probably. A lot of people do that, 8/10. Okay, well, I mean, it's just a way of writing numbers that we decided how we write them, so who says that's not the right way to do it? Well, if this were 8/10, and we'll put a question mark over it, if, okay? Well, we just described what 5/6 was and what 3/4 was, and so the result should be 8/10. Let's look at what 8/10 is. It's 8 parts of something that's been divided into 10. So let's see how good my dividing things into 5 skills are. Pretty good. So 8/10 is this much thing. Now, would you be satisfied for me to say, take this much of one thing and this much of another thing, and you get this much of one thing?
No, doesn't relate to each other.
Well,
They look the same.
does it look right is what I'm asking. Does it look reasonable?
Yeah.
Or to take these pieces, really it does. I mean, take one of these pieces.
The bottom one's supposed to be double the top ones.
Yeah.
Because they're added.
Oh, I see.
Yeah, yeah.
Huh?
Yeah.
What?
I don't think they understand, like, that's supposed to be twice as big as the other ones.
Mm-hmm.
Because it's them added.
Twice as big? No, 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 no. No, this is the
It
same.
should be the same size as them.
It's the same. It's not twice as big. It's the same. Right? That's what we're saying. We're saying these are wholes, right? These are entire things. So this is 5/6 of an entire thing, 3/4 of an entire thing, and we're theorizing that we have 8/10 of an entire thing. Does that seem right? Does that look right? I mean, take one of these pieces right here, put it right there. It's already past an entire thing. You do even more. You have a whole thing and some more. Like you can see visually a counterexample, okay? Knowing that that can't be the way you add fractions. Okay, and here's the reason. When you say 8/10, let's just back up to 8. You have 8 things. Okay, here's 5 things, and I want to talk about that with these. You can see, even visually, this thing right here, this piece, is not the same as this piece. So if I try to say I have 8 of them, what would I say I have 8 of? 8 what? Okay. Imagine this. I have, that's a tomato. It's supposed to be an apple. They're cherries. Okay. And you have 3 oranges. Okay. And so I go to say the sentence, I have 5 what?
Fruit.
Okay.
But not the same size.
That you could say you have 5 fruit, but if you just add these together and say you have 8 fractions, or that's not gonna fly.
Well, you
Right? We're
only
gonna be more
have
specific.
5.
The analogy breaks down, right? I can't do anything to make these things the same. Okay? What I'm trying to get you to see is that they are 2 different things. We can't do anything about this example, but we can do something about these examples. The problem with these, the thing that's making these different is what? What makes these things different from each other?
You have parts that
What?
you have different amount of parts that we're in.
Different amount of parts, the size of the parts is different, right? You can't compare them. Now, I can't slice these up and make them comparable, but I can slice these up and make them comparable. I can cut these pieces in such a way, and these pieces in a slightly different way, so that all the pieces are the same size, right? And one surefire way to do that is say, well, this piece was cut into, or this thing was cut into 6, this thing was cut into 4, so I'll just do like the same thing to both of them. I'll cut this one into 4 and this one into 6, right? So if I cut all these 6 pieces into 4 pieces, and these into 4, this into 4, this into 4, and I come over here and I do these pieces into 6 pieces each, well then I'll have the same amount of pieces in both pies, let's say, right? Does that make sense? So if I cut these into 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, then how many pieces will there be? How many? 24, because you got 6 right now. You cut each of them into 4. We know our multiplication. 6 times 4 is 24. If I come over here, 4 of them. If I take each one and cut it into 6, I'll have 24. Right? Now they're the same thing. That's what common denominators is about. It's talking about the same size pieces. That's all it's talking about. Okay? So we could do that, and visually it would be difficult to do. They'd be really, really tiny. Just go back. Yeah?
No, you said it was 24. Well, wouldn't you take the least common
That's,
wouldn't that
yes.
be 12?
I'm right and you're also right. Right? And what you're saying is more efficient.
Okay.
And what I'm saying is less efficient. But it gets us there.
Oh.
So we'll get there, and then we'll talk about let's be more efficient than that. Okay, so we're gonna do it the less efficient way because visually it's easier to see.
Oh.
Visually we can see the simplest way is just cut this into 4 each, cut this into 6 each. So we're sure they're the same. That's just a better way to do it. We can see it better than their numbers.
Yeah.
So here, we'll cut each of these pieces, all 6 of them into 4 pieces. Obviously, those 5 pieces we're going to be cutting into 4 pieces, so there's 4 times as many. Okay. This we're going to do 6 on both. And numerically now, so we can see it conceptually, we can see it pictorially, and so this is, and in the numbers, what we see we're doing, we're multiplying by a fraction on each of them. We're going to multiply by 4 over 4. What's 4 divided by 4?
1.
So what am I multiplying this by?
1.
Multiplying this by 1. What happens when you multiply something by 1?
Same.
It's the same. It doesn't change the value of the number. So 5, 6 times 4 fourths. It doesn't change the value of the number. That's important. You can't just change the values of numbers that you're trying to manipulate. But it also makes it so that I can compare it with the other one. Same thing here. This is a 1, doesn't change anything, everything's okay. So here we get 20, 24ths. Here we get 18, 24ths. We add them together and we get 38, 24ths. But now since, as Tyler brought up, I didn't do it as efficiently as possible, at the end we tend to do what with a fraction like this?
You're gonna. You have to. Yeah.
Oh.
Mix the number.
Okay, we'll talk about that. But before even making it a mixed number, what do we
Simplify.
simplify? Okay, I like the word
Yes,
simplify.
simplify.
Okay, so I'm gonna put a little arrow here, and I'm gonna say simplify. Now, maybe this is just an old math teacher thing, but what's another word people use instead of simplify? Do you know it?
Solve.
Reduce?
Reduce.
Reduce. Have you heard reduce before? Okay, reduce, it's just it's a misleading word. A lot of students have been found to think that when you reduce a fraction, you make it a smaller number. Are you making it a smaller number?
No.
It's the same size, just
Smaller fraction.
smaller numbers involved. But the ratio of this number to that number is the same. So, what can we divide these by?
Man.
2, at least 2.
Yeah.
19 over 12. Okay, that's as simple as we can simplify it. Let's talk about that mixed number thing.
Yeah.
Yeah.
Okay? Mixed numbers.
Let's.
What are they good for?
Nothing.
Well, they are good for something. I won't say they're good for nothing, but they're good for something. The thing they're good for,
You only use them in math.
well, I would say you can't use them in math.
Oh.
In math, we don't use mixed numbers because if I want to add 2 fractions together, do I want to add 2.5 to 5 3/4? No, I want to make it, what do we call it? What do you call this? Improper. You make it an improper fraction so that you can add it. If you multiply 2 fractions together, how do you multiply 2 fractions together? What's that?
Using improper fractions.
Well, like I'm saying,
Reciprocal.
if we have 3/4 times 5/7, how do we multiply those?
You gotta
Or you use the
cross
opposite.
multiply.
Whoa, okay, we're gonna have to come back to that. That's not clear yet.
Cross
We're gonna come back.
multiply.
Here's what you're gonna, when we look at that, here's what you're gonna learn. To make fractions useful, so that you can use them, so you can manipulate them and interact with other numbers, you always make them one integer over another integer. You never have 2 5/8 or whatever, and actually do something with it. So if you can't do anything with something, would you call it useful?
No.
No. Okay, so in math, it's not very useful. But where is it more useful to say 2.5 rather than 5/2?
It allows you to compare more directly to our numbers.
Yeah, if I want to tell you how many dollars I owe you in change, I don't say 5/2 dollars. I say $2.50, $2.50, right? That makes more sense. I want to know how many holes there are and then how much more there is past that hole. Okay? So I don't want to hear 525/63, right? I want to hear how much is it, how many holes are there, how much is there left over? Okay, that makes sense. So to look at it and to quantify things, that makes more sense. But if you actually want to use a fraction in math, you got to make it improper. Okay, one integer over another. Whether you're going to add them or you're going to multiply them, that's what you'll find. Okay, so there's a more efficient way to do this from the beginning, and that was what, Tyler? What do we call that? Rather than just multiply the denominators together. What did you call it? Find the what?
You find the least common multiple.
Least common multiple, least common denominator, same thing. So I need a pen. 3 5/6 plus 3/4 more efficiently. We wouldn't multiply 6 by 4 and 4 by 6.
By 3.
But by 3. So we multiply 4 by 3
You get 12.
and 6 by
By,
2
Yeah,
because we
two.
can get them both to be 12. And there won't be any simplifying to do. There won't be canceling this factor of 2 out. Okay? So we'll multiply this by 2 and this by 2, or sorry, 3, because we can't throw off the value of the number. So we're just multiplying by 1, multiplying by 1 in a more efficient way. So 10 twelfths is 9 twelfths is 19 twelfths. That's more efficient. Oh boy. Okay. So now we're going to multiply. Okay. This is tricky to explain. So 3/4 times 5/7. Some of you were saying, well, some of you said cross multiply. So let's get at that one first. Cross multiply. So that would mean multiply 3 by 7 and 4 by 5, and get what? What would be the numerator?
You would know.
Yeah, it's not really clear. There's not really a process here. Let me just point out what you're thinking. You're remembering this phrase, cross multiply. It's this thing that was drilled into you as young people, and you have forgotten when it's applicable, and it's not applicable here. Okay, where it's applicable is in proportions. Remember proportions? A proportion is one fraction set equal to a fraction. Not that we want to multiply them together. We want to solve something like 2/3 equals x over 9. This is a cross multiply situation. Okay. You were taught multiply 2 times 9, multiply 3 times x, divide, x equals 6. That's cross multiply. And I'm not really a big fan of cross multiplying because, let's just back it up. You'll find out that I'm not a fan of things like cross multiply or PEMDAS or FOIL or all these things that are designed to help you remember stuff that is not, you don't need to memorize it. You just need to know how numbers act and how they interact and how they combine together. All right? And if you know about solving equations, which you do know a thing or two about because I looked at your tests, and several of you, most of you solved at least the simpler equations without too much difficulty. Graphing part, lots of people struggle with the graphing. So here, we've got a number divided by 9. How do we cancel out that 9?
With multiply 1 by
You
9.
multiply by, multiply by 9 over 1. And those 9's cancel. 9 divided by 9 is 1, and so it's all gone now. So multiply this side by 9 over 1 as well. 9 divided by 3 is 3, and 3 times 2 is 6. We don't need cross multiply. We don't need people to handicap us and tell us the rules for doing things. When all you need to know is that this is an equation, And what does it mean for me to say that what is this symbol communicating? What?
They're the same.
What's the same?
That
The
the
whole
way the two
whole-
numbers relate to each other.
The two sides are the same thing. This thing is the same as this thing. If we were to use a balance, like an old-timey balance, right? You put one thing on one side, put the other thing on the other side, they balance each other out, okay? They're the same, okay? So the even do the same thing on both sides becomes this mantra that you repeat over and over, and you memorize, and you lose sight of what it means. We do the same thing on both sides because if I, to cancel out this 9, multiply this side by 9, I just made this side 9 times bigger than it used to be. If I just out of the blue make this 9 times more massive than it used to be, what's going to happen to this side?
It should be heavier.
It's going to be heavier, it's going to go down. Okay? We can't have that. So if we make one side 9 times bigger, we make the other side 9 times bigger. So we multiply both sides by 9. Now both sides are still balanced. Okay? That's a convenient thing to do because we cancel out the 9s, and now this side is just x. So 9 times bigger than this side, it's just one of the x's. Right? And that's what we do. So that cross multiply and do both things on the same side, or the same thing on both sides. It can be debilitating. It can take away from your abilities and assume that you don't know how to do what we're asking you to do. Okay. So let's come back to this problem. So what did we learn just now about multiplying these together? Don't want to cross.
Don't cross that.
Don't want to cross multiply.
Yeah. Straight cross.
It's easier to go straight across. It is how you do it. You just go straight across. 15 over 28. And that's it, 15 over 28. 15 28. 3/4 times 5/7 is 15 28. Any questions about multiplying two fractions together? The only other thing I can say is something like 3/4 times 7/9. You could just multiply straight across, but
Reduce
what's that?
simplify.
Simplify. Because what's going to happen is all the factors of the numerator are going to be combined with the factors of this numerator, and likewise for these two denominators, and so we're just going to have all the factors multiplied together, and then we're going to wind up having to cancel out any common factors in the end anyway. So if there's any common factors between this numerator and this denominator, since they're all about to become part of the same fraction, you could cancel them like that, which saves us just a little bit of time. Because it's easier to cancel 3 with 9 than 21 with 36. I'm trying to find that common factor. So we can multiply fractions. How do we multiply fractions?
Straight across.
Straight across. Numerator times numerator, denominator times denominator. So, with fractions, we have added them. And by that reasoning, could we subtract them?
Yep.
And it's all the same, right? 5 6 minus 3/4. Let's see, we have 10/12 minus 9/12. We get 1/12. Okay. So we can do that. We can multiply fractions. We multiply straight across. Zip it up. What are you doing?
I was just kidding.
You're making noise.
Just get a piece of paper.
So we can add them, we can subtract them, we can multiply them, and what's left?
Divide.
Divide them. Okay, so let's say we take 3/4 divided by 5/7. Okay? And this is important. Make sure you know where that is. Okay, so how do we divide fractions?
You multiply by the reciprocal.
Of what one?
The other fraction.
So this is the fraction and this is the other fraction?
Yeah.
Okay. So multiply by the reciprocal, so what's that gonna look like?
3/4 times 7/5.
That's right, and we multiply them straight across.
Great.
That's correct,
I
okay?
remember that.
Now, mistakes can be made, so let's just talk about mistakes that happen. One thing, especially if you write it like this, 3/4 divided by 5/7, and you just remember multiply by the reciprocal, you forget which one is supposed to be the reciprocal of. And this will happen from time to time. Does it make a difference?
No.
Yeah.
This is, we know the right answer, 21 over 20.
Oh.
What do we get here?
20
over
over
21. It makes a big difference. You get the reciprocal of what you were supposed to get.
Mm.
Okay? Now let me help you see why, at least like a little proof, that this does work, and it will work every time. So let's say if it's written like this, I would just encourage you to write it like this until it's so second nature that you'll never make that mistake again. So let's write it like that. And so we learned from our finding the common denominator, we can multiply the numerator and denominator by what?
1.
Well, you can multiply the fraction by 1, which means the numerator and denominator are the same. So if we multiply the numerator by the same thing as the denominator, it's okay. Right? Nothing changes. We didn't hurt anything. So if I multiply the denominator by 7/5, is that something nice happen when you do that? It's what?
It's 1.
It becomes 1. 5 times 7 is 35. 7 times 5 is 35. 35 divided by 35 is 1. When you divide by 1,
It's the same thing.
same thing. Divided by 1 is the same thing. Okay, so that's nice. Down here, this just has become 1 in the denominator, 1. Okay, but I can't just multiply by 7/5 in the denominator. I have to
Do the numerator.
numerator as well. 7/5. Okay, so you get 21 over 20. And we divide 21 20ths by 1. It's the same thing as we've already said. 21 over 20. That's the solution. Okay. If I tried to do it the other way, like if I, instead of multiplying by 7/5, I multiply by 4/3. Well, I wouldn't get a 1 down here, get a 1 up here. And that's not even any nicer to look at. Right? 1 divided by, I would get 20 over 21 down here. Which would be equivalent, that would be true. 1 over 20 over 21 would be the same as 21 over 20. But that multiplied by the reciprocal didn't work. So it's by the reciprocal of the denominator. So just at least some justification as to why we multiply by the reciprocal of the denominator. Right? Any questions, Cody? Squeaky noise. So what your name is now?
Squeaky.
Is there a song
You can
already?
turn anything into a song.
Yeah, squeakle.
Squeakle? Okay. Any questions about anything so far? That's like fractions from 1st to 5th or 6th grade in 10 minutes. Is it in there? Do you have any questions? Okay. You're welcome to come and ask me questions on an individual basis. I'll run you through that as many times as you want. But I think you'll stop winning it after a while. You'll just learn it. So come and ask me questions individually, and in class now, I'll spend very little time talking about why we get common denominators, why we multiply by the reciprocal of the denominator, and all that kind of stuff. All right. So next, we have exponents with a pen instead of not a pen. Exponents. So here's an exponent. Let's say 2 squared. What does it mean when I square 2?
You multiply it by itself.
Multiplied by itself. 2 by itself. 2 to the third.
2 times 2 times 2.
2 times 2 times 2. It's just, this is, let me just show you something. 2 plus 2 plus 2, this gets old, right? Alright, so we learned addition and then we learned how to add a bunch of things, one right after the other, but that gets old. So how do we shorten this?
To do a square power.
Well, let's back up a little bit.
There's 4 twos.
4 times 2, or 2 times 4, it doesn't matter, right? There's 4 2's. 4 2's added together. Yeah? Okay, so 2 times 4, we can do that. Well, then we can do, so this is repeated addition, and now we have 2 times 2 times 2 times 2. We want to shorten that up, because that gets old after a while, right? And so then we shorten that up with 2 to the 4th power. The 4 up there is just a shorthand of repeated multiplication, just a shorthand of repeated addition. So 2 times 2 would be 2 plus 2. 2 times 2 times 2 would be 2 plus 2 plus 2 plus 2. And anyway, you get the idea. So that's what that little guy up there means. So here's one thing that I noticed. If I say x squared, okay, I want you to block this off. I'm going to take this and I want you to evaluate for x equals -4. What does that mean, evaluate for when x equals -4?
Yeah.
So this now becomes -4 squared. So this is what I see a lot of times when I ask people to do that now. Is that right?
No.
No.
Well, I'm going to put -4 there. What's wrong with it?
You set it up right, but you have to do the math still.
Did you do the math?
Yeah.
Okay. What do I get then?
16.
16? Or if I square 4, I get what? 16, and then I put a negative. Which is it?
No, it's 16 because there's 2 negatives times each other with positives.
Yes. Now is this doing the same thing as this?
Yes.
No, because they don't have a negative.
So all this together, I want to evaluate that for when x equals -4. Did I do that? Did I evaluate x equals -4? Well, if I get 16, yes. This says, what does this really say? What should I really get if I do this? Okay, so let me just make this clear. Okay. So, and we're going to watch another video, I think, because I think we'll have enough time. What this all comes down to is an agreement. We've all agreed. Well, for one thing, we agreed that writing, think of how strange this is. Like, we've all agreed that if I write a 4, but small, make sure it's small, and put it up here, then it means to do this. There's nothing inherently, like if an alien saw 2 and a small 4, it wouldn't think, you gotta do that. We have agreed, those people who are using Arabic numerals and use the widely accepted math, that's what we agree a little 4 up there means, right? Well, according to that, if I put an exponent next to a number, I do, I apply it to that number. So if I put this 2 to this 4, what does that mean? It means 4 times 4. And then what does this mean? It means multiply by negative. And what should I get? I should get -16 if I write this down. Now, is that what should I get when I plug -4 into here?
No.
No, it's not. Okay? Because this means x times x, right? And what is x? It's -4. So I should get -4 times another -4. Right? So the problem is, according to how we've agreed to write things down in math, I've not told you that I want a -4 times another -4. I've told you I want a 4 times another 4, and I want the whole process to come out as a negative. Right? So we just we borrow from English, we use parentheses, and now that means just what you wanted it to mean. And that is a -4 times another -4. That is positive 16. Okay? It's important. It's important how to write these things. And especially if you're over-reliant on your calculator and you write down -4 squared, one person might understand that like that it's just their notation to themselves, and they know I'm going to square -4 and I'm going to get positive 16. But if you just write that down and you're not paying attention and you don't really get it, and you do -4 squared, every calculator will tell you 16. Because calculators are computers that need to be told exactly what to do, and they do things according to very specific rules. And if you put a 2 there, it's only going to apply to the thing that's right next to it, which is just a 4. You need to put parentheses around that if you want to convey that you should square the whole thing. Okay? But that's a whole other thing that we're going to look at. So just be careful when you're using exponents, and you're, and especially with negative signs, watch out. Now, something, I don't know if you want to use the word interesting, but I think it's interesting. How about x to the third and say x is equal to -2? What we should do is multiply 3 x's together, which means what should that come out looking like if we put -2 in there? It should be negative, yeah. We should get -2 times -2 times -2, and we should get -8.
No.
No.
Whoa.
These two are positive, then this will make it negative. But what if I do this?
Oh, yeah.
Wrong incorrectly, right? -2 to the third. What will I get then?
Then you get positive.
Will you?
Yeah,
2 to the third
which is 8.
is 8, and then what? Make it negative. -8.
Whoa. What?
This way you get negative times negative is positive, and then times another negative is negative. Here, if you just take 2 to the third, you get 8, and you multiply by negative, you still get -8. Either way, I guess you can't go wrong. That's why I try not to ask questions with odd powers when I want to see if you know what you're doing with exponents. Because if it's odd, whether you do it incorrectly or correctly, you come out with -8. There's no way to get around it, unless you just force it to be +8. All right. Yeah, I'm gonna watch a video now. Talked about evaluating. I guess there's just one more thing that we should talk about before I play the video for you. And the book calls this simplifying algebraic expressions. An algebraic expression is one that has variables in it. Okay. And you probably call it combining like terms. They're the same thing. Okay. So combining like terms looks like this: 4x plus 2x. Well, what about these are alike? Why do we call them like terms? With what?
They're both being multiplied by x.
Both being multiplied by x. We got what we really have. Well, we just talked about it. This is shorthand for repeated addition. I have an x plus an x plus another x plus another x. That's 4 of them, right? Add 4 of them together. That's just shorthand for that. Okay. Then 2x is just x plus x. Now what am I doing with 4x and 2x? Adding them together. Well, okay, I'm just adding 6 of those together. 6x. Okay, so we get that. We've got like terms. There's 4 of a thing, there's 2 of a thing. I can say I have 4 teddy bears and 2 teddy bears. I have 6 teddy bears. They're all the same thing. Now what if I had 4x squared plus 2x? What is it? Can we combine like terms here?
No, we can't.
We can't. We can't combine like terms here. We're done. If we were asked to simplify, you'd say it is as simple as possible. Okay. Let me show you what some people want to do. We attempted to do it, and then I'll prove it. Show you that you can't do it. So people wanted me to call this 6x to the third. It's not a majority of people, but it's enough people that it's worth mentioning. 6x to the third. I don't even know how to start to talk about this problem. So let's just, maybe we'll take the 4 and the 2 out of it. And we'll go x squared plus x. That somehow feels a little bit better. I feel a little bit more okay about just calling the x to the third. Just combine the exponents together. 2 1. But the problem with that, it comes from just writing it out the way, what it actually means. We have x times x plus another x. That's what this is saying. Okay? A big question mark. Could these be equal? Well, on this side, what does x to the third mean? X times x times x. X times x, it's almost the same. So far, it is the same, but x times x times x. This is x times x plus another x. At the very least, you should see addition and multiplication aren't the same thing. These can't be equivalent to each other. And in another sense, like these are two completely different concepts. X could be represented as a length, right? X, length x, right? This room is x wide, whatever. Okay. And we talked about multiplication, how it could be like the area. So if that length is x, this area is x by x, and so the inside area would be x squared, x times x. So how can I add x squared with a length x? They're not the same thing. You can't. They're not like terms. So what's the definition of like terms? How do I know things are like terms? They have the same. I can put these together, right? This is 6x. How about, what if I put a 2 there? Can I put those together now? What is it? 6? So now we're running into the same thing. It seems to make more sense to say to the fourth, but you run into the same problem as before, right? X, even if this is squared, that means x times x. You know, is this x to the fourth? No, this is x times x. We add x times x. We don't get x times x times x times x. Right? Just got to think about what it means. But what we really have is some amount of something and some amount of the same kind of thing. Right? Apples and apples. There's 4 apples, 2 apples. How many apples altogether? 6 apples. The same thing, right? They don't become kumquats. They just say apples, and there's just 6 of them. Okay? So if we're going to combine like terms, I think a couple things would suffice. What do we need to be the same here? Powers? Powers. Gotta have the same power, same exponent, and the same variable. I think that, we might not have got that because it's kind of obvious, but it's necessary to say. So, gotta be the same variable with the same exponent. Now we can put them together. And hopefully you see how come. Why can't you put those things together? And this is not about like terms, what I'm about to say, but there is a time when we add the exponents together. Let me just show you when that is. It's just, well, if I want to take x squared and x squared, and I want to combine them somehow to get x to the fourth, well, what is x to the fourth? It's x times x times x times x. We've said this so many times I won't ask you to repeat it. Well, this is x times x, and this is x times x. What do we need for this to be the same as this? You multiply them together. So when we're multiplying them, then we can add those together. And that works for x to the third. Right? Now this becomes x to the fifth. Whenever you multiply two things together with exponents, you can add the exponents together as long as it's the same variable. But that, like I said, it's not like terms, not simplifying algebraic expressions. That'll come a little bit later. Okay. So now we're supposed to talk about order of operations. And I put a couple of questions on your test that I want to talk about. First, I'm going to play this video for you. He's going to show us an ad, so.
chip it off.
If you went to elementary school in the US, or much of the rest of the world, you almost certainly learned about something boringly called the order of operations. A set of rules for whether or not you should do multiplication before addition or addition before subtraction to get the right answer on your math test. Except you don't always get the right answer, or even one answer. I mean, is 8 minus 2 plus 1 equal to 5 or 7? And is 6 divided by 3 divided by 3 equal to 2/3 or 6? The problem is, focusing on the order of operations can lead to ambiguity and obscures the real, underlying, and often beautiful mathematics. A mathematician will tell you that 8 minus 2 plus 1 is really 8 plus negative 2 plus 1, which is unambiguously equal to 7, even though the so-called order of operations standard in the US tells you the answer is 5. If you want 5 for your answer, then you really need some parentheses. But why is this ambiguity even possible? It's because fundamentally, all of these operations are simply different procedures that start with two numbers and combine them in some way to give you one number. Each operation takes two numbers as input, 2 and no more. If you want to be entirely unambiguous and pedantic, every single pair of numbers in any algebraic expression should be inside parentheses. And then there's no need to know any order of operations. Just evaluate the innermost parentheses first and work outwards, collapsing them down pairwise like a championships bracket. But it turns out that's not the only way. It's possible to change the order in which you do the operations, to rearrange the parentheses, as long as you know what the underlying mathematics is. For example, if you want to add 3 plus 4 and then multiply the result by 5, you can either do the addition first and get 7 times 5 equals 35, or you can do the multiplication first, as long as you know that multiplication distributes across all the terms in the parentheses. That is, 5 times 3 plus 5 times 4 equals 15 plus 20 equals 35. The same answer. And how do we know multiplication distributes? One way is to draw rectangles, but I've done that before. The same rearranging can be done for exponentiation and multiplication. 3 times 2 all squared, or 6 squared equals 36, is the same as 3 squared times 2 squared, 36. It even works for addition and subtraction. 5 minus 1 plus 2 is 5 minus 1 minus 2. So the true order of operations is this. Use parentheses and learn what exponentiation, multiplication, addition, and the rest are really doing. Then you can proceed however you want. That's not to say that we don't have a conventional order of operations in mathematics. I mean, deciding that we evaluate multiplication before addition allows us to get rid of lots and lots of redundant parentheses. And noticing that 1 plus 2 plus 3 equals 1 plus 2 plus 3, and 2 times 3 times 4 equals 2 times 3 times 4 removes a ton more. But the point is that those parentheses are still there, still implied, just like how 3 minus 4 is secretly implying 3 plus negative 4, and 3 divided by 4 is really 3 times 1/4. But anytime the result might be ambiguous, you really need to use parentheses. Then you can proceed in whatever order you want. The order of operations learned in school, however, is different. It's a mechanical set of instructions that dictates just one of the many ways you can do algebra. It locks you into a single path through the beautiful mathematical landscape, which, while necessary for a computer whose goal is merely to give you the right answer, doesn't really give any insight onto what it is that you're doing when you do algebra. So while the order of operations isn't technically wrong, because most of the time it'll give you the standard answer, it's morally wrong, because it turns humans into robots. This Minute Physics video was brought to you by Squarespace, the all-in-one platform that makes it fast and easy to create a professional website.
Okay, so I pretty much agree with this guy too. I mean, there's this PEMDAS thing. Let me ask you this. I'm going to bring this back up and put up a simple problem and ask you just to work on your own for just a minute and tell me what the answer to this is. Just write it down and figure out what the answer is. Whoa. Well, that's what you're saying. You have it written down? No. Jake's gonna see the work. Gonna see what you're doing. You're to be uninfluenced by other people. Just come up with your own answer. survey. Just seeing what you got. What you got.
Yeah, now I'm screwed up. Yeah, I wanna go the other way.
Well, hopefully we've got a few answers. So one answer that's very common is 144, and another is 2. And that's because you could, well, I think we'll all agree that you add these two together first. They're in parentheses, and so that's clear. That's been communicated. Okay? Here's where the two diverge. You could do 48 divided by 2 is 12. Multiply by 12, you get 144. Or you can do 2 times 12 is 24. And 48 divided by 24 is 2. Now, the point of the video and my point is, neither one of these is righter than the other one. Inherently, mathematically. Right? The problem with this is it's poorly written. It's like a confusing sentence where you're not sure what person is talking about. Is the he talking about that he or that he? It's a poorly worded, it's not a sentence, it's not a mathematical sentence. We need an equation, an equal sign to that, but it's ambiguous. What does it mean? What does it want us to do first? Okay? Now, he says it's not to say that there's not an agreed upon, there's not a standard order of operations that we teach. And do you need to go earlier? Okay. Right now? Okay. Okay. There is a standard that most people follow, but here's the problem with this one. The main argument is, do you do this division first or do you do this multiplication first? What do you think? Multiplication first or division first or multiplication first? Division first. Multiplication first. Division. And multiplication. Well, you cannot do two things at once. Like he said, 2 numbers only. Only 2 numbers interact at any one time, so you have to decide which 2 are going to interact. So which ones? Division?
Isn't it
Division left to right. Okay, so that's the way I learned. And when I first saw, there was a video where this guy, he posts lots of upper level math and physics stuff. So when he posted this and said, what's the answer to this? He said he got stuck on this. That's ridiculous. And I did it and I got 144. That's what I would get. And I thought, how silly. And then I looked, and it had only been posted for just a little bit, and there's already like 500 comments on people at you. You don't know what the answer to this is. This is what it is. Like, really passionate about the way they found it. And you know what it came down to? Why they found it the way they found it?
Personal preference.
My teacher told me that's how you do it. My calculator said this is how you do it. There isn't a right way, an inherently mathematically right way. There's an agreed upon way. And the one that I agreed upon, and the one that the book adheres to, and the one that I'll assume that we'll use will come out to 144, okay? But don't think that that's the right way and that there's wrong ways. I don't ever want to see you on a YouTube comment fight saying, no, this is how you do it. I want you to be the person that says, this is poorly structured. It's really not clear what the person wants you to do. They could want you to divide by this first. I would, if I wanted to be really clear that I wanted to divide first, or to multiply first, I would put parentheses there. But really, if I wanted to be really clear, I would make sure to put parentheses around that first. It's not clear. Because here's the main problem. Some were taught this way. Absolute hierarchy. Parentheses first over everything. Exponents over everything below it. Multiplication before division. Addition before subtraction. Okay? You were taught, and I was taught, I think, like this. Right? Equal playing field. Left to right. These are the same. Right? It just matters what you decide, what you agree upon. Okay? There's no mathematical reason why this represents this many. It's just two squiggles put together, and we just agreed that this will be this. These three things, right? So it's just all about an agreement. The order of operations that we will follow, though, does fit this mold. Go from left to right. You do get 144. But if you look on your test, number 13, we got like 1 more minute, maybe 2. Look at number 13 or 14. I put a purposefully ambiguous question in there. Let's look at 14. 7 plus y divided by 10x when x is 2 and y is 43. Now, clearly we should add these parentheses, what's in the parentheses first.
This is the previous classes.
What?
Pass it down. They're not ours.
Oh, I didn't pick them up. Okay. Well, this is 50. Obviously, this is 50.
Yeah.
Right? We can even put parentheses over there if we wanted to. Okay. Now, as I've written it here, what would you do first? If we're going to do this, which I'll just inform you that it's totally ambiguous and I decided on it, but that's what we're going to do. What do you do first? Divide, left to right. Divide first, multiplication on the same level. So 50 divided by 10 is 5, times 2 is 10. But look back at the original problem. According to the answer key, the person who wrote this wanted you to get 2.5, 2.5. They wanted you to multiply 10 times 2, right? Well, that's kind of clear because usually when we write 10x, it's a group, right? They're together. They are joined at the hip, 10 times x. But when you replace x with 2, it's not that clear, right? So if they really wanted you to do that, what they should have done, especially if they're going to follow this, is unambiguously put the parentheses around it. Or don't use this symbol. This symbol is terrible. Use this one. Not unclear. Very clear. Add these together. Multiply these together. Do that division. Right? So just some discussion about math and education, how we teach it, how we learn it, how people can get really mad about it. Right? Pretty fun stuff. Your homework is over there, just the first 2 sections. Or no, the one, yeah. First 2 sections. Sorry, these were taken up real estate on your desk.